Okay, we're going to take a look at alcohols and phenols in the context of a laboratory experiment and consider properties and physical and chemical properties of these compounds. So first of all, for alcohols, there's a classification of alcohols. We can have a primary alcohol where the hydroxyl group is on a primary carbon. So for instance, ethanol is a primary alcohol. If the hydroxyl group is on a secondary carbon, then you have a secondary alcohol. So isopropanol or 2-propanol by the IUPAC name, that's a secondary alcohol. And if it's a tertiary carbon, that's a tertiary alcohol if the hydroxyl group is on that carbon. So if we have a T-butyl group with a hydroxyl, that is tertiary butyl alcohol, or its IUPAC name would be 2-methyl 2-propanol. And of course you cannot have quaternary alcohols, because if it was a quaternary carbon, there's already 4 bonds to carbon. Now phenols are a special case. They look like alcohols. The hydroxyl group, however, is on a benzene ring. Now, we call that a phenol. It's a functional group distinct from a normal alcohol. The thing is that phenol itself is a specific compound. So if you talk about phenol, the compound, it is simply a benzene ring with a hydroxyl group attached to it. This compound on the right is a phenol as a functional group. So we have a phenol with a methyl group and an isopropyl group on the ring. So this is 2-isopropyl 5-methyl phenol. They are both phenols, but the one on the left, its name specifically is phenol. Alcohols and phenols have hydrogen bonding due to the hydroxyl group. And of course, they have a nonpolar portion, the hydrocarbon, as well. When we look at solubility, say in water, the smaller alcohols, methanol, ethanol, and propanol, they are miscible. You see the infinite solubility? That means it will dissolve in any quantity. You can have 50-50 alcohol and water, methanol, ethanol, or propanol, or any ratio of water and those 3 alcohols will be a solution. As you get to butanol, notice that there's an actual solubility. You can dissolve some butanol in water, and it's the hydroxyl group that's interacting favorably with the water through hydrogen bonding. But the hydrocarbon chain now is 4 carbons long, and it doesn't interact favorably with water. And so you have a maximum solubility. You can dissolve that much butanol in water, and then you exceed the solubility and it will form a separate layer. And as the hydrocarbon chain increases to pentanol, hexanol, the solubility in water goes down because the hydrocarbon chain is getting longer and the favorable interactions with water are being countered by increasingly unfavorable interactions with the nonpolar portion. Now, if you go to hexane, which is a hydrocarbon nonpolar, methanol, the smallest alcohol, has limited solubility. The hydrocarbon portion is very small. The OH, the hydroxyl group, does not interact favorably with hexane, a nonpolar hydrocarbon. The hydrocarbon chain of methanol is not large enough to counteract that unfavorable interaction. But once you get to ethanol, the hydrocarbon chain is long enough to interact favorably with the nonpolar hexane, and we have miscible solutions. So it's only methanol that is not miscible with a nonpolar solvent like hexane. Another property is that phenols are relatively acidic compared to alcohols. So why are phenols more acidic? If we look at the pKa's, we see that phenol is a pKa of 10 compared to 18 for cyclohexanol. So it is 10 to the 8 times more acidic. Remember, pKa is a logarithmic scale. One difference in pKa is a factor of 10 times more acidic. So if you try to react cyclohexanol with sodium hydroxide, you get no reaction. The alcohol is not acidic enough to be deprotonated by the hydroxide ion. Phenol, however, its pKa is low enough, it's acidic enough that it will react with sodium hydroxide, and we get the phenoxide ion. This would be sodium phenoxide. Of course, the other product would be water. The hydrogen from phenol and the hydroxide from sodium hydroxide make water. So why is phenol more acidic? Well, if you form the phenoxide ion, you have the O-, but that can move through resonance to form other resonance structures. So we have multiple resonance structures for the phenoxide ion. And remember, when you can spread that charge out, delocalize the electrons, you lower the energy and make it more stable. If we try to make this alkoxide ion, this is less stable because the negative charge is localized on the oxygen. It cannot move through resonance and lower its energy by occupying a larger volume. By the way, you can make an alkoxide ion. This is quite common. How would you do it? Well, you do an oxidation reduction reaction. You use sodium metal, for instance, and you end up with the alkoxide ion and hydrogen gas. And so clearly you're going to need 2 of these. So the goal of this experiment is to have some alcohols that are unknowns, and we're going to do a series of tests that examine the chemical properties of these alcohols. And we're going to find that primary, secondary, and tertiary alcohols and phenols react differently to these tests that we have available to us. And that will allow us to do the identification of our unknowns. So the first one I want to talk about is the Lukas test. And this is for distinguishing between primary, secondary, and tertiary alcohols of low molar mass. If you have a primary alcohol, you get no reaction. If you have a tertiary alcohol, you get a reaction that is relatively fast. The secondary alcohol is a reaction, but it is slower and may require heat, but you do get a reaction. We have a substitution, an SN1 reaction. And during an SN1 reaction, you form a carbocation. And if it's a primary carbocation versus a secondary carbocation versus a tertiary carbocation, the tertiary is going to be most stable. Remember, tertiary carbocations are the most stable, primary are the least stable. So if this mechanism, an SN1 reaction, proceeds through a carbocation, then we are going to observe this trend that tertiary alcohols, which form the most stable carbocation, will react the fastest. Secondary alcohols will form secondary carbocations, and they will react more slowly than tertiary alcohols. Primary alcohols, at some point in the mechanism, will form primary carbocations, which are not very stable. And in the time frame of the Lukas test, we observe no reaction. This can also occur by an SN2 reaction, but it's much slower, so you have to let it sit a much longer time. And during the time frame of our test, you will not observe the primary alcohol to react. So you can see here a picture in the lower right. The negative test is on the left, and the positive test is on the right. And when you look at the negative test, it looks just like one layer and it's transparent. So you might have, say, a primary alcohol and there's water. Where's the water from? Well, the hydrochloric acid and the zinc chloride are dissolved in water. The Lukas test is for low molecular weight alcohols. Of course, if the alcohol becomes very large and the hydrocarbon portion is very large, then you're going to have two layers. And that might make the test a little more difficult if the alcohol will not dissolve into the water. If you look at the positive test on the right, the picture, what do we have in the test tube there? If we have a positive, well, now you see two layers. And in the bottom, we have our water, and of course the zinc chloride and the HCl that are dissolved in it. And you have your alcohol. Okay. But what is this top layer now? What is that top layer? Well, that is our product. You might have, for instance, tertiary butanol. If that was your alcohol, now becomes 2-methyl-2-chloropropane. But that no longer has hydrogen bonding capabilities. That is not water soluble. Hence the second layer that is now floating on top of the aqueous layer. This is where larger molecular weight alcohols might be more difficult because they're not 100% soluble in the water, and you're going to have a layer due to that to begin with. So you can't really focus on that. But there is another feature if you look at that test tube. It's cloudy. So it's not a very transparent liquid in the bottom there. It's very cloudy, very hazy. So that is a mixture of the aqueous layer and some of the product, which is not very soluble, which is not soluble in the water layer, and it hasn't made its way up to the upper layer yet. So you have these two liquids that are wanting to separate and they haven't quite done it yet. So you get this haziness. The next test that is used to distinguish between primary, secondary, and tertiary alcohols is the chromic acid test. And here we see the opposite trend. Tertiary alcohols give no reaction, but secondary alcohols and primary alcohols do. And this is what you look for. A negative test is orange. That is the chromium in solution. This is a +6 oxidation state. In the product of this reaction, chromium is +3, and that's a blue-green color. So this is an oxidation reduction reaction. So chromium goes from +6 oxidation state to +3. That's reduction. If you have a primary alcohol, that will oxidize to an aldehyde. But an aldehyde will further oxidize to a carboxylic acid. So the primary alcohol, when it oxidizes to an aldehyde, we lose one of the hydrogens and we form the carbonyl. There's more bonds to oxygen from that carbon. It's been oxidized. And there's still a hydrogen on the aldehyde that can be replaced by an oxygen to form the carboxylic acid. If you have a secondary alcohol, there's a hydrogen there, you can oxidize this and form a ketone, but there is no further oxidation because there's no hydrogen on that carbon to be replaced by an oxygen. You'd have to break a carbon-carbon bond to oxidize that carbon further. And for a tertiary, there is no hydrogen on this. There's no hydrogen on this carbon. So there's no reaction. You would have to break a carbon-carbon bond to add a bond to oxygen from that carbon. And that will not happen. So under these conditions. So we have no reaction. So if you have an aldehyde, go back to the primary alcohol. If you start with an aldehyde, you can oxidize that to a carboxylic acid. If you start with a ketone, then you cannot oxidize that. So we are actually looking at oxidation of alcohols, primary and secondary here, and also of aldehydes. If you start with the aldehyde, you can oxidize that as well. Sometimes people will say, oh, I have a positive test because the phenol showed reactivity. So they might say, oh, the phenol has a positive reaction. It reacts, but it doesn't give you the results that you expect. This oxidation of a phenol to a quinone is slow. So what happens is the quinone starts to form. You start to see a darker brown from the product, and this maybe like a tarry substance, depending on the specific phenol. So you do see change. You see something happening, but it's slow. And while this occurs, you start to see the product of the organic being oxidized. There's still a lot of chromium 6 around, masking the new chromium 3 that's forming. So you don't really see the bluish green color unless it sits around for a long time, and then the chromium 6 finally starts to get used up. So yes, it is a reaction that you see, but it's not a positive test because it's not indicating a primary or secondary alcohol. I guess you could say it's further evidence of a phenol, so it is useful in that regard. For the phenols themselves, we have the iron 3 chloride test. Iron 3 is the ferric ion, so you might hear it referred to as ferric chloride. So what happens is we get this reaction where the iron becomes bonded to the oxygen, and that forms a compound having color. And that color can vary depending on the specific phenol. You can have phenol itself, or you can have different phenolic compounds. Depending on which one you have, the color will be slightly different. So it can be green, blue, purple. So I grabbed this picture from the internet, and you can see cyclohexanol has no reaction. It's got that yellow color. We did not get the color change. Phenol, you can see the color change. It's become bluish, violet kind of color. 3, there's no reaction. There is no phenol in that compound. And in 4, you can see there's a dark purplish color there. So that's a positive test for a phenol. The acidity of the phenol can be used as a test as well. So if you use pH paper, you dissolve the phenol in water, and you get this ionization in water. It's a weak acid. It's not going to ionize 100%, but this equilibrium sets up, and the formation of hydronium ion lowers the pH. So for alcohols, they might be around 5 for pH, and phenols 3 to 4. So the pH will drop a little bit. Alcohols in water are probably going to be around 5, maybe, thereabouts, maybe 5.5, because solutions sitting out in air absorb carbon dioxide, which becomes carbonic acid. So water sitting in the environment is normally on the slightly acidic side, and then you add an alcohol. It doesn't change that, but a phenol will lower the pH relative to that of an alcohol.